This is KVS Naidu, lecturer in mathematics, Miriam College, Amalapuram. In this session, I would like to explain some special types of rings. Some special types of rings. Those are integral domain, division ring, field. Integral domain. First one, integral domain. A commutative ring or with unity containing no zero divisors, containing no zero divisors is an integral domain. Is an integral domain. A commutative ring or with unity containing no zero divisors is an integral domain. For integral domain, we simply use the word D. We simply use the word domain. Simply is the word domain. We simply use the word domain. It is denoted by D. It is denoted by D. In condition notation, D plus comma dot is an integral domain if and only if first one D is a ring, second one D is commutative, third one D has unity element, fourth one D has no zero divisors. That means integral domain a commutative ring or with unity containing no zero divisors is an integral domain. For integral domain, we simply use the word domain. It is denoted by capital D. In condition notation, D plus comma dot is an integral domain. First one, D is a ring. It satisfies the R1, R2, R3, R4, R5 and R6. D is commutative, that means AB is equal to BA. The property AB is equal to BA satisfied. Next, D has unity element. 1 into A is equal to A into 1 is equal to A. D has no zero divisors. That means AB is equal to 0 implies A is equal to 0 or B is equal to 0. A is equal to 0 or B is equal to 0. This is the definition of integral domain. Next, example of integral domain. The ring Z of integers is usually integral domain. The ring Z of integers is usually integral domain. That means Z is the plus positive number. The set Z is equal to minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on. This is the set of integers. It satisfies is a ring. Already we proved one is the identity element, one is the unity element. Next, for all A comma B belongs to R, AB is equal to BA, AB is equal to BA, AB is equal to 0 implies A is equal to 0 or B is equal to 0. Already we proved. Next, Z is equal to is an integral domain. Next, Z is 6. 0, 1, 2, 3, 4, 5. Z6 comma plus comma dot, where Z6 is equal to 0, 1, 2, 3, 5. Under the multiplication and addition modulo 6. System under the addition modulo 6 and the multiplication modulo 6. This is the Z6. One is the unity element. Next, AB modulo 6 is equal to BA modulo 6 for all A comma B belongs to R. A comma B belongs to R. Next, 0 divisors. 2 comma 3 belongs to Z6. 2 not equal to 0 and 3 not equal to 0. 2 not equal to 0 and 3 not equal to 0. 2 multiplication modulo 6 6 is equal to 3. 2 multiplication modulo 6 3 is equal to 0. 2 into 3 multiply 3 divide 6. One time remainder 0. So the product A not equal to 0 and B not equal to 0. The product AB is equal to 0. So Z6 has 0 divisors. Z6 has 0 divisors. Therefore, Z6 comma plus comma dot. Z6 comma plus comma dot is not an integral domain. Is not an integral domain. This is the example of integral domain, not an integral domain. Usually R plus comma dot comma Q plus comma dot is also integral domains. R plus comma dot, Q plus comma dot are the integral domains. This is the definition of integral domain. Next, division ring of skew field. Division ring or skew field. Division ring or skew field. Let R be a ring with unity element if every non-zero element in R is invertible under multiplication. Is invertible under multiplication. Is invertible under multiplication. Then R is division ring. R is division ring or skew field. Let R be a ring with unity element if every non-zero element in R is invertible under multiplication. Then R is division ring. In condition notation, R plus dot is division ring if first one R is a ring, second one R has unity element, third one every non-zero element in R, every non-zero element in R is invertible. Is invertible under multiplication. That is the definition of division ring. Condition probability: R is a ring with unity element. R plus gamma dot is a division ring. R is a ring. R has unity element. Next, every non-zero element in R is invertible under multiplication. Multiplicative inverse definition: let R be a ring with unit element 1. Let R be a ring with unity element 1. A non-zero element A belongs to R is said to be invertible under multiplication. There exists B belongs to R such that AB is equal to BA is equal to 1. AB is equal to BA is equal to 1. B is the multiplicative inverse of A. B is the multiplicative inverse of A. Let non-zero element A belongs to R, then exists B belongs to R such that AB is equal to BA is equal to 1. This is the multiplicative inverse. Next definition, field. Next definition, field. Let R be a commutative ring if unity element, if the unity element, if every non-zero element, if every non-zero element in R is invertible under multiplication, then R is a field, then R is a field. Let R be a commutative ring with unity element if every non-zero element is invertible under multiplication. Then R is a field. In notation, condition notation, F plus comma dot. It is denoted by F. It is usually denoted by F. F plus comma dot is a field if and only if first one F is a ring. F is a ring. Next, second one, F is commutative. Third one, F has unity element. F has unity element. Fourth one, every non-zero element in F is invertible under multiplication. Invertible under multiplication. This is the definition of field. This is the definition of field. Let R be a commutative ring with unity element. If every non-zero element in R is invertible under multiplication, then R is a field. It is denoted by, it is usually denoted by F. In condition notation, F plus comma dot is a field. First one, F is a ring. It satisfies the R1, R2, R3, R4. Next, second one, F is commutative, AB is equal to BA. Third one, F has unity element. 1 into A is equal to A into 1 is equal to A. Every non-zero element in F is invertible. That is AB is equal to BA is equal to 1. B is the multiplicative inverse of A. This is the definition of field. Next, theorem. This is the definition of field. Theorem. A field has no zero divisors. A field has no zero divisors. No zero divisors. Proof. Let F plus comma dot be a field. Let A comma B belongs to F. Let F plus comma dot be a field. We prove that F has no zero divisors. No zero divisors. Let F plus comma dot be a field. We prove that F has no zero divisors. Let A comma B belongs to F. A not equal to 0. A not equal to 0. A comma B belongs to F. A not equal to 0 belongs to F. F is a field. F is a field, there exists. F is a field, it satisfies the condition. F is committed, F is a ring, F is committed to, F has unity element, every non-zero element is invertible. There exists, every non-zero element is invertible. So A not equal to 0 belongs to F. There exists A inverse belongs to F. A inverse belongs to F such that A into A inverse is equal to A inverse into A is equal to 1. A into A inverse is equal to A inverse into A is equal to 1. Suppose AB is equal to 0. AB is equal to 0. A not equal to 0. Suppose AB is equal to 0. A not equal to 0. Multiply A inverse left on both sides. A inverse into 0. By associative law, A inverse into A into B is equal to 0. A inverse into 0, 0. So A inverse into A is equal to 1. 1 into B is equal to B. B is equal to 0. Thus, A comma B belongs to A. AB is equal to 0. A not equal to 0. That implies B is equal to 0. A comma B, AB is equal to 0. A not equal to 0. B is equal to 0. We prove that. Let F plus comma dot be a field. We prove that F has no zero divisors. Definition of zero divisors. AB is equal to 0. That implies A is equal to 0 or B is equal to 0. So, we prove that A not equal to A comma B belongs to F, A not equal to 0, A not equal to 0, F belongs to F and F is a field. There exists, F is a field, it is every element, non-zero element is invertible. So, there exists A inverse belongs to F such that A into A inverse is equal to A inverse into A is equal to 1. Suppose AB is equal to 0, A not equal to 0. Multiply A inverse into B is equal to A inverse into 0. A inverse into A is equal to B. B is equal to 0. Again, similarly, suppose A comma B belongs to F. B not equal to 0. A comma B belongs to F. B not equal to 0. B not equal to 0. F is a field. B not equal to 0 belongs to F. F is a field. There exists B inverse belongs to F such that there exists B inverse belongs to F such that B into B inverse is equal to B inverse into B is equal to 1. B into B inverse is equal to B inverse into B is equal to 1. Suppose AB is equal to 0. AB is equal to 0, B not equal to 0. Multiply B inverse right side 0 into B inverse. 0 into B inverse. That implies by associative law B A into B inverse is equal to 0. A into 1 is equal to 0. A is equal to 0. Therefore, thus A comma B belongs to A. B not equal to 0, that implies A is equal to 0. Therefore, AB is equal to 0, that implies A is equal to 0 or B is equal to 0. A is equal to 0 or B is equal to 0. Therefore, F has no zero divisors. F has no zero divisors. That implies I will explain. Again, I will explain. A field has no zero divisors. Theorem: a field has no zero divisors. Let F plus comma dot be a field. We prove that F has no zero divisors. That means AB is equal to 0, A is equal to 0 or B is equal to 0. AB is equal to 0 or A is equal to 0 or B is equal to 0. Let A comma B belongs to F, A not equal to 0. A not equal to 0 belongs to F. F is a field, so exists invertible. So there exists A inverse belongs to F such that A into A inverse is equal to A inverse into A is equal to 1. Suppose AB is equal to 0, A not equal to 0. Multiply A inverse on left side, A inverse into A, B is equal to A inverse into 0. A inverse into A by associative law, A inverse into A is equal to B is equal to 0. 1 into B is equal to 0, B is equal to 0. Thus A comma B belongs to A. AB is equal to 0, A not equal to 0, B is equal to 0. Similarly, we prove that AB is equal to 0. AB is equal to 0. B not equal to 0. A is equal to 0. Thus, A comma B belongs to A. AB is equal to 0 and B not equal to 0. AB is equal to 0, comma B not equal to 0, A is equal to 0. Therefore, AB is equal to 0, A is equal to 0 or B is equal to 0. F has no 0 divisors. Already similarly we prove that a division ring has no 0 divisors. A division ring has no 0 divisors. I will continue the next class. Okay, thank you.